Let's see.
Can you hear me?
Hey, good to see
Good
you.
morning.
Are you at UCSB right now?
Exactly. It's been a
Oh,
busy week.
yeah, I bet. Yeah, it's been cool. Haley, who sent me? Somebody sent me a photo of the flume yoga going on. It's pretty sweet.
Yeah. We'll soon be going back to the lab.
Huh.
Yeah. We just introduced our microplastic to the flip system yesterday.
Oh, cool.
Yeah. So we'll be taking some of our samples today.
Oh, awesome. Yeah, take lots of photos. I really want to see all the nitty gritty. One of my
Yeah.
favorite things to look at is like little plastic particles floating in turbulent water. I had this jar that I used
Yeah.
to,
It's really cool.
yeah, just full of like plastic and water, and I just shake it sometimes.
Yeah. Yeah. I'll follow because I'll be leaving very soon, but I'll be following as I go.
Yeah, sweet.
Yeah. Well done.
Looks like we got quite a few people joining right now. Welcome. We're just gonna give like a minute or two and then get started here. I did send out an email with this link, but I'm gonna drop it in the chat here too for everybody to get started with our studio download if you haven't done it already. I'm gonna walk you through it at a pretty basic level. Just how to do like the fast install. One of the things I've been realizing lately from these really big collaborative training sessions is that when you have 30 people trying to use Open Specy all at the same time, the site kind of gets bogged down. And so our studio is going to make that seamless because everybody's going to be using their own computer to run the app. All right. Well, I think we can at least get started with the RStudio tutorial. So I'm going to share my screen here and just walk people through how to install RStudio. So I'll paste this link in the chat again. Okay. So to install RStudio, if you haven't used R before, don't worry. I promise this is a very easy way to set up Open Specy. It's literally just, I think, 2 lines of code and a little bit of clicking. And this is going to make your use of Open Specy a lot more reproducible because unlike if you're using the Shiny app, which is at www.openspecy.org, you're welcome to use that here too, but I definitely would prefer that some people start using the app on through R, because when we have too many people trying to use the website simultaneously, it starts to get bogged down. And so to install R, what you'll do is you'll click download and install R here. And then depending on your operating system, so you have Linux, Windows, I'm a Windows, so I'd click that one. And then I'd click install R for the first time. And then download R 4.4. And if you get this, then you may need to click download the unverified file. Let's see here. But usually it doesn't pop up with that. I'm actually surprised that it flagged that. Now RStudio, here you can download RStudio. I'm also getting a flag for that. I must have like some advanced safety settings or something on, but I can still download them. And then you'll walk through. I'm not going to actually click these executable files because once I click them, it's going to overwrite my previous versions of R. But basically, you'll open up this one and open up the RStudio. So it's 2 different softwares that work simultaneously. The R is basically the workforce of RStudio, which is kind of like the scaffolding where you can view and interact with R code. And so you'll click those and you can just use the default settings on everything. And it really should just take like a minute or two. Maybe while people are doing that, I'll just be available. I'll wait a couple minutes while people are installing those. If you have any questions or challenges while you're doing that, let me know. Basically where I want everybody to get to, whoever is going to be following along is to get to this. Let's see here. Get to this screen where you have RStudio open. And while we have all these cool people here, feel free to post in the chat, like where you're from, who you are, what kind of spectra you get stoked about. My favorite spectrum is HGPE right now, because I've been building a lot of visualizations and tutorials with a specific spectrum. But And don't worry if getting R installed becomes a problem for you. You can use the Open Specy website, the web tool for this tutorial today. But in future tutorials, so be focused on. Oh, cool. Today we're going to be focused on batch spectroscopy, which is usually when you're doing batch spectroscopy, it's going to be around like hundreds of spectra to maybe 1,000 spectra. When you're dealing with even larger sets of spectra, you're usually dealing with spectral maps. And so in the future tutorials, we're going to start working with spectral maps. And you can do some tiny spectral map analysis in Open Specy, but we're actually going to start using the R code console to do a lot of our analysis, because it's just really challenging to actually visualize data sets that are about a gigabyte in size. It's really challenging. So we will be using R in future tutorials quite a bit, and I'll be walking you all through how to do that kind of analysis. Thank you, Maddie and Brittany and Julian, for commenting, and Barbara, nice to see you. FTIR tire rubber spectra. That's a tricky one. You are a master for going after that one. Let's see. We got some polystyrene spectra. Yeah, that's a good one. I like that one. Yeah, it's okay if you don't have a favorite spectra yet. You'll get to know your spectra really personally at some point, and then you'll have your favorite. Oh, ABS. Oh, interesting. Yeah. All right, sweet. Well, good to see you all on here. Okay, so is it safe to assume that people have R open at this point? Does anybody need any help? If you want to raise your hand, at any point you can just unmute, talk, or raise your hand, or add a comment in the chat. I'll be watching all of those. Okay. All right. Hearing nothing, maybe everybody's like already in R Pro, so I will move forward. So the main package that you're gonna need is the Open Specy package. So you'll go into Tools here at the top, and you'll type in Open Specy, and yeah, I'm gonna have to restart because I'm developing the Open Specy package constantly. All right. So now, so in this, you have in RStudio, for those who aren't familiar with it, you have different windows. So these are different files that I have open. I'll just make this simpler so that it looks like what other people are probably seeing in here. And you have different windows. So this is your coding console window here. This is where you can kind of like write script out. And then you can run it, and when it runs in the console down here. And so you'll be getting like outputs of, okay, this is the information that you requested. Here you go. Let's see. Let me just close all others. There we go. All right. All right. So with as with all code or data management, you always want to be saving your files. So I'm just going to save this one to my desktop and call it Open Specy, run Open Specy. R. And what that'll do is basically, like, in the future, if I want to run Open Specy on my desktop, I can just click that on my desktop here. Let's see. Oh, you can't actually see it because it got saved on the other window. Yeah. So there's like there's this file here, and I'd be able to click that, and then it would open up in R. And so, like I was saying, this coding to run the app is actually very simple. It's just a few lines of code. So the first line is library Open Specy. And what that's going to do is it's going to install all of the functions for Open Specy. And then the second one is run app. And what that's going to do is it's going to grab the most current version of all of the libraries, the Spectral libraries, and the Open Specy Shiny app, and install it on your computer. And then it will actually run that, like it'll pop up here once it's done. So now we are running Open Specy on our desktop. And one of the nice things about this is that you're leveraging the full power of your system. So on the Open Specy website, we have a basically it's a computer that's shared by everybody who's using it, and it's a it's like a normal desktop computer basically. But if everybody's trying to use it at once, it kind of gets bogged down and slows down and lags. Also, the website, I'm constantly updating, so you may see changes, and then when you analyze it one day, you might have slightly different results than the next day. I try to make sure no major changes are happening like from day to day, but there are definitely changes that are happening on the website. Versus this, if you run the app from your own desktop, it's going to be totally stable unless you reinstall Open Specy and decide you want to rerun the app, like repull the app from scratch. It'll be stable. It'll just be one version that you're going to be leveraging. One thing I should have said in here, if this might have been confusing for folks when I was running this code, I was clicking Control Enter so I clicked on the line and clicked Control Enter, and that's what ran like each of those lines. I could have also clicked the source button. That would have run all of the lines, or I could have clicked the run button, which runs just like the line that I'm on. Okay. How do we update the R desktop version of Open Specy? Great question. So to update the R desktop version, what you do is you would reinstall the package. So you would reinstall the package, and if you did it like this, it will update the package. And then you'll have the newest version. Usually new versions don't come out more than monthly. Actually, CRAN does not allow us to push new versions more than monthly unless we have some sort of like really big reason to do that. So yeah, if you wanted, let's say you always just wanted to use the most up-to-date version of Open Specy, another thing you can do is you can have it like this, install.packages, and then I think it's Open Specy like this, and then that's your code that you run every single time that you run, and then you'll guarantee that you're going to get the most up-to-date version of Open Specy package and the Shiny app. So different use cases for different people. Yeah, thank you very much for the question. All right, so so the main thing I wanted to touch on today, does anybody else have any other questions about getting the Open Specy loaded on their desktop? If you haven't been able to get that, then feel free to use www.openspecy.org. That's totally cool. You can use that whenever you want. And just pulling up some notes here. Okay. So we're going to be talking about, last time that we got together, we talked about single spectra analysis, which is, we have one spectrum, we want to identify what it is, we want to process it, and we walked through exactly how to do that. In this one, we're going to be talking about, well, what if we have hundreds of spectra, thousands of spectra that we want to analyze simultaneously? Open Specy can do that too. And so I'm going to just use a basic example, but you can grab an example that works for you of multiple spectra. So you want to find like quite a few spectra. Let's see here. All right, so I will show you the spectra that I have. So I have these 28 spectra here. I wonder if I can give you these through the site. Let me see here. Maybe I can email these to everybody real quick and think that through. Is it possible to? No. One sec. Let me create a shareable link for this. All right. Okay. Here we go. So I'm just okay, it looks like one person may not be able to access this file. If anybody has trouble accessing this file, what I've shared is a zip folder full of HDPE spectra that was shared by my colleague Rachel Kozlowski for doing this analysis. And while y'all are downloading that zip folder, I just want to walk you through like why this data set? Why am I analyzing this data set using batch analysis? So some of the things to think about, one is that it should all be pretty similar spectra, like collected in the same way. All this spectra, this is transmission FTIR spectra that was collected with the same settings. If you're using Raman and IR and a bunch of different settings, and your spectra is just all over the place, it's going to be pretty unwieldy to do batch analysis on it because in batch analysis, we're not fine tuning the process one spectrum at a time. We're doing one process to all spectra. And so if you have, let's say you have some spectra that need to be converted from transmission to absorbance units, all that stuff, like when you're collecting your spectra, try your best to collect it in a very consistent way, and it's going to make this batch analysis easier. Once you see how fast this batch analysis goes, you're gonna be like, oh man, I really need to start collecting my spectra like that if you're not already, because it really moves so fast. Like spectra, doing single analysis spectra, um, single analysis is going to take 5 minutes or something like that. You can do 1,000 in 5 minutes, and if they're all super high quality spectra that have top hits, you just download your data and you're ready to write your paper, versus sitting here in every single spectrum, like fine tuning the analysis of it. So and I'll show you that. So hopefully, are there any questions at this point? Try to keep pausing. Okay, I'm not seeing any questions. Awesome. All right, so it's two different ways that you can upload batch spectra to the Open Specy interface. The first way is you could just have your files and highlight all of them and then drop them in Open Specy. And that will upload all 28 files. The second way is that you can have them in a zip folder like this, like the one that you downloaded, and you could just upload that zip folder. It'll do the same exact thing. It's just going to read all the files in the zip folder. And what you'll see here right off the bat is that there's this new component that maybe if you haven't done batch analysis yet, you'd be like, what is that? Why am I seeing this image with a bunch of colors on it? And what this is it's actually a spatial projection of your data. So we had, I think it was like 28 spectra in here. And basically every square in here is a different spectrum. And I think this is my perspective right now, why we're doing this, is that this is a really easy way to kind of quickly navigate your data set. And I'll show you some tricks you can use to try to amplify your understanding of what's going on in the data. So the first one is you might want to investigate the signal to noise of all your spectra at one time. And so I want to look at the, I'm going to add in, so we have the pre-processing tab up here. I'm going to add threshold signal to noise. And then I'm going to set the minimum value to 4, which is basically, so for those who might not have been here last time, the signal to noise value is the highest peak divided by a low region. And typically, the minimum you ever want that to be is about 4. If it's lower than that, you probably just have pure noise. And so what we can see is that in this signal to noise, we also see a histogram of all of our values. We could have a higher threshold too than 4. I just set that as the default just because it's a good kind of lower bound. Oh, okay. All right, so we have one issue. Something went wrong with reading the data from uploading the zip data file. Have you tried unzipping the data file and then just kind of grabbing all of the files, like highlighting them all, and then dropping them like that? See if that works. And if that doesn't work, let me know. Okay. Somebody else has the same issue. Yeah, I'm wondering why it might be doing that. Are you using the website or are you using the desktop version? Desktop version, huh? Yeah, I'm kind of confused. Did you have you updated your Open Specy library recently just to make sure we're all using the same library? Could do like install packages Open Specy again, just to see if that fixes things. Yeah, sorry about that. If that doesn't work, what I would recommend is just trying to follow along, download the test data set, or maybe even the test map. You could download the test map and then upload that, because that really should work. Like if that's not working, that would surprise me. So yeah, the test map is going to also be a batch analysis that you can download this test map and upload that over here. Sorry about that. Are some people, just to check, like, is everybody having this issue right now, or are some people able to keep going? Okay, seems like it may be a couple of us. Okay, working for some. Okay, great. Got it working in the zip file format. Okay, awesome. Thank you. Thanks for that. All right. Okay. And for those who get really stuck on something, please send me an email after. Let me know like what you're seeing, and I'll try to fix whatever bug is occurring. I just may not be able to do it like super fast on the fly for everything. All right, so we're gonna go back to this thresholding signal noise. We have our threshold here is this red line, and then the signal to noise values are here. It's a histogram of them. And what we can do is if we increase this minimum value, let's say 10, which is actually a much more common value to use in spectroscopy. 10 is like the gold standard. If you have above 10 signal to noise value, your spectra is very high quality. And so if we do that, what we see here on this map is that some of the boxes end up getting blacked out. So, and also here it says good signal, only 93% of our spectra have good signal. So one of the things that you can do is you can actually go in and use this to fine tune your pre-processing procedures to amplify that signal. So I can look at these spectra and see, like, does this spectra look like it should have good signal? So this spectra does look like, this looks like a quality spectrum. I'm not super concerned about it. It's definitely higher noise than, you can see here, it's definitely higher noise than some of the other spectra that aren't getting blacked out. But it's still quality enough to analyze for sure. So let's say that I wanted to try to fine tune that a little bit. One thing I might try to do is I might try to smooth the spectra a little bit more to increase the signal to noise. And to do that, you can use the smoothing derivative procedure, and you can increase, there's two different things you can do. You can increase this wave number window or decrease the polynomial. So if we increase the wave number window, let's see what that, oh, yep, okay. That fixed one of them. Let's see, oh, nope. Okay, increasing the wave number window a little bit ended up getting one of them back, but the other one is still kind of not going to be changed by that. Let's see, so I could go here, and now this one is passing the signal noise threshold that we set. This one's still not passing. We could play around with it quite a bit, but honestly, you know, signal noise ratio of like 6, I think it's usable. So I would move forward with it, but I just wanted to show you like how you're fine tuning the processing procedure for all of your spectra simultaneously. And it's really good to set rules and be like, all right, if I'm not above this threshold, then that spectra, maybe I say this one's unknown. 1 out of 28, I don't know what it is. It's too high noise. I'm not going to trust it. So that might be one conclusion that you come to. You come here, you play with the settings a little bit. Oh, okay, I was able to get one more of the spectra on board. The other one still not increased enough. I'm gonna ignore that one, or maybe you do some special processing just to that spectrum, but you don't worry about it for the batch analysis. Okay, great. I'm glad to hear that the Open Specy desktop update worked for you. So, all right. So that's kind of the vision for, and in the last training, we went over every single one of these tabs. So I'm not going to go over all of the details today about that. But if you do have any specific questions about these tabs, please do let me know. One common thing, actually, let's see. Yeah, it looks like we have some CO2 interference in this spectra. So we could add in the flattened region. So the CO2 peak is around here. And flattened region will turn that into a flat line, this region here. And in some of the spectra, it was looking like, in this one specifically, it was actually quite a large peak that was there. And you don't want to be identifying CO2, you want to be identifying your material that you're looking at. But CO2 has such a high fluctuation in the environment around your instrument that you end up getting that signal in there all the time. And it can be tricky to deal with. So I'd add in flattened region. And when you're doing batch analysis, you really kind of want to be just like, you're looking at the big picture of your spectra. I'm clicking around. I'm like, okay, do I see any artifacts that are kind of consistent? I'm seeing another one over here in the lower region. I'm seeing a big spike, like a baseline spike, basically. And that I do not think is actually part of the signal that I'm looking at. Yeah, actually, no, that could be the HDPE peak that's in the lower region because it's so consistent. I might need to look that one up. I'm not gonna remove that one yet. But if I did think that that one was something, a lot of times near the edges of your spectra, you will have these artifacts where there's either high noise or high baseline, and you can restrict the range by going in here and saying, okay, I don't want to look at anything below 850, let's say. So I'm going to make the minimum wave number 850, and then the maximum wave number is going to be 4,000. And then I'm going to add that in, and now I've wiped out that lower peak over there. I do think I'm thinking now that actually is part of the polyethylene peak, because they have two peaks in the lower region between 2,000 and 500, and I think we just may be like on the cusp of it, of the second peak over there. So I'm not gonna remove that one, but that's another common artifact that you'll want to be looking at in your spectra to make sure that you're not having that issue. Another thing you can do is kind of toggle on and off the pre-processing so that you can see how that changes the spectra. So like, is this a well-processed spectrum is kind of the big thing that you're trying to figure out. Are these pre-processing settings, are these appropriate for my data? One thing you'll notice is that all of the squares just turn blue. And when that happens, it means that all of the values are below your threshold. So if they're all one color, then everything's too high noise, basically, right now is what we're looking at. So everything's, much less than 4. All right, and so I can toggle this on and off just to look at one of these signals to make sure that I'm getting the peaks that I'm expecting here. So now I'm seeing this lower peak. I do believe actually that this is a legitimate peak over here. And it's a little bit more clear to me when I'm looking at the raw spectra compared to the process. I can look at another one just to make sure that, that seems like it's being amplified correctly. And the default settings of Open Specy are really clutch because they amplify your signal to noise very quickly, and it still looks a lot like what you would expect from a highly processed absorbance spectrum. And that's what we're really getting after. And it has high ID accuracy. All right. Okay, so in here, once we start getting into identification, you can, there will be some additional selections that you can toggle through to change the coloring in this heat map here. Before we go to identification, I do want to show you how to download your process spectra, because this is going to be an important part of defending your analysis, is showing like, okay, you have your raw spectra, of course, and then you want to have your process spectra that you analyze. And so you can download your spectra, and that will be whatever the pre-processing settings are at the time. That will save a copy of the fully pre-processed data set. I can show you what that looks like real quick. It's in a bit of a unique format, and it's really because we're trying to preserve metadata. But basically, the format for our 28 spectra, so in the format of the data set, you have wave number value on top, and then any metadata should be at the end. So there's XY position, file name, column ID, session ID, file ID. That's some metadata. And then you have wave number values here for these columns. Any columns with numbers in them are wave number values. And then you have the intensities going across. So for a lot of people, this format of spectral data is very convenient. And so maybe it'll work for you right away. If you need it in a different format, you can use the R package. The R package reads in this format, and it'll export it in other formats, JSON, RDS, CSV. We have like a ton of different other formats that you could export it as. All right. And similarly, if you've never downloaded your library spectra, I would also encourage you to download that spectra. So that will download whatever library you have selected here. And I'll just go over the library selections real quick. So by default, we have the derivative transformed library selected for both Raman and infrared. But there's a no baseline, so a baseline corrected library for both Raman and IR. There's a derivative for just IR or Raman, just Raman derivative. There's a FTIR no baseline and a Raman no baseline. And then there's some different AI. These are more experimental libraries that we're working on right now. So usually when you're doing identification, you want to use a library that is consistent with the way that you process your spectra. That's like, if you get nothing else from this training, it's just like, that's the number one thing. The more consistent you can be between your library spectra and your unknown spectra and how you process them, the better. So we're going to do FTIR derivative, because these spectra are derivative transformed. They're an absolute first derivative transformed spectrum. And you can download. So if we wanted to download that, it's always good practice. Why is that me see. I need to have this actually opened for it to download correctly. So I just clicked identification and it's going to start analyzing the spectra right away. So it's going to analyze all 28 spectra at once. Let me see if this will work now. Yeah, here we go. Okay, so I guess you had to have identification selected for the download to actually work on your library spectra. So once you've selected that, then you can save your library spectra as a CSV also. And then you have all the components to be able to reproduce all of your research. You could use a different software to do it. You could use the Open Specy R package to do it. Lots of different options. All right, so we have now an identification heat map. So the map has actually changed. We're no longer looking at the signal to noise ratio. We're now looking at the ID for the spectra. So, and similarly, there's still some blacked out boxes here. And that's because they're below our thresholds. If I were to remove the threshold signal to noise, what that will do is it will remove that as a filter. Basically, it will not black out the pixels based on signal to noise, but it will still black out the pixels based on this correlation threshold, 0.07. And so this spectrum is not above 0.07 correlation threshold. It actually looks like not a very good correlation. So it's good that that one did get flagged. Correlation thresholds become really important when you're doing batch analysis. I definitely suggest using a correlation threshold, using the 0.7. It will avoid false positives. If you have a study that you're actually concerned about false positives, you may want to set that correlation threshold lower. So I've seen as low as maybe 0.6 being accepted. But any lower than that, and you're really getting into the range of just like, you don't know, you're very unconfident about what the identification is, like how good of a match they are. And so primarily I use 0.7. All right, and I'm not super dogmatic about the signal noise threshold. I probably would leave it lower because a lot of times it's hard to actually, we have an automatic signal noise thresholding routine, and it's hard to get that to be perfect. And so sometimes it will flag data that has good signal as not having good signal. So I'm not super dogmatic about that, but I do think it's useful, especially if you think that you may have lots of spectra that is high noise. And 4 is generally a good like lower bound to kind of suss out like, oh, is this going to be a problem or not? All right. So there's some different colors that we can filter by here. So right now I have the signal noise threshold going, the correlation threshold going. This spectrum is being flagged as not a good ID based on the signal noise and correlation threshold. I can hover over it. It says that the signal noise ratio is 13, but the correlation is 0.67, which is kind of on the cusp. And when we looked at it, we said, oh, that's not really a good ID. So I'm glad that that flagged that. When I hover over the other values here, it's popping up as saying in the Z here, it says that it's polyolefins. This one says other plastic. And all of these are really high correlation strength. So if I click this one, you know, we can see really good, this is really good confirmation between the known and unknown spectra. This is about as good as you're gonna get. I would look at this and I'd say, yep, that's a match. You know, that's classic. Some of these that are coming up as other spectra, other plastic, sorry. Other plastic is a class that we use as a catch-all. because there's a lot of plastic that are hard to categorize. So it'll be like somebody sent me this like polyethylene with like 50% additives or something. And I don't know, should that be in the polyethylene class or should it be in, the additive class, or like how do we categorize that? So we throw a lot of things into the other plastic. So when you're doing this batch analysis, you may need to go and do some further digging into the other plastic. And what you can do is you can actually look at the exact information on here. So what does it say here? This one's just, the only metadata is that it says that it's some other type of plastic. We could look at the top hits to try to find like another hit that's not other plastic. So here we have polyolefins is also quite a high hit. And like I said, these are HDPE spectra, so they are polyolefins. So you can reclassify things like that. And let's see here. Look at another other plastic example. This one's also other plastic. So this one's coming up as HDPE also. All right. And then some other things that you can look at. So you can look at the correlation strength heat map here, and you can see, so any of the really bright areas, those are going to be super high correlation, and any darker areas are going to be very low correlation. So this one is like the highest correlated. It should be the most classic identification. And then this one's kind of on the fringe. It's like not super confident in it. This was one of the ones that had pretty high noise in it. I would still be confident in this ID because I'm recognizing that region as being noise. But this is one of those you may want to consider classifying as unknown. And this one too, as classifying as an unknown, because it is very low correlation. And when I look at it visually, it looks like a bad match. I'm missing a lot of the peaks here. So there's different approaches that you could do, and I recommend like set up your plan for how you're going to batch analyze your spectra and just stick to that plan, write it up in your research methods, and be very consistent about how you're processing the spectra. Don't make sure not to bias towards certain classes of material types. And so one thing that you could do is you could say, all right, I'm going to visually QC every spectrum. So I'd go through and I would say, all right, look at that one. Looks good. Looks bad. Okay, I'm going to flag that one. Row 26, flagging that one. I just write it down or add it into a spreadsheet. Okay, 27. One looks good. Looks good. Looks good. And you can see how fast this goes. Like even doing a manual QC of your spectra in batch mode is super fast. Probably what I would do, to be totally honest, is I would just investigate the ones that are getting flagged based on my thresholds. So the ones that are really low correlation, I would investigate those. So I would only investigate, if I was doing this analysis, I would just investigate the 2 really low correlation threshold ones further. And then I would kind of look at the big picture of the spectra, like we did when we were pre-processing at first. Like, are there artifacts that I'm seeing across my spectra? Is the spectra being processed in general in a good way? You do need to have that level of intuition and not just trust that this is working 100% for you. Because if you trust it 100%, you're giving away a lot of your ability to make very accurate decisions about the spectra. So you definitely want to develop an eye for analyzing the spectra and assessing the matches. And especially if you're just getting into the analysis, I'd recommend starting with single spectrum analysis and just like spending a few days kind of working through it and understanding how does spectra get get processed? How does it get analyzed? Play around with some of the pre-processing settings on the tool so that you can really gain like an intuition about how to analyze this information. And then you'll be ready to set your rules that make sense for your spectra and your pre-processing routines that make sense for your spectra. And then once you have that, it should be a lot faster. Like when I'm going through, I analyze, 1,000 spectra at a time pretty regularly. I'm not going in and manually assessing 1,000 spectra at a time. That would take me like weeks of effort. I set rules that I'm going to follow. If it's below this correlation threshold, I will QC it. If it's above that, I'm going to trust that it's working well. If it's below this signal noise threshold, I'm going to suspect it and inspect it further. All right. So let's see. Is there some couple other options for looking at your data here? So one is the match ID. The match ID is basically the individual library spectrum that's being related to in your data. So for some applications, you may find that you really want to know, like, what is the exact library match? Because if all your spectra is getting matched to one library ID, it could be that that library has like a unique artifact or something like that. That one library spectrum has a unique artifact that's kind of strongly influencing your spectra. So if this was all the same color and all of my spectra was just getting identified to one library ID, I might suspect it as being maybe an incorrect pre-processing procedure or even an incorrect library entry. And if that's the case, please email me and let me know that you found something that might be incorrect, and we'll get it fixed. All right. Okay, and then so you can also still look at your signal noise ratio here. And oh yeah, some new things have popped up here. So right now we have good correlations and good identifications. So good correlations, that's the percent of spectra that are above our correlation threshold. And good identifications are the percent of spectra that are both above our signal noise threshold and our correlation threshold. And in general, you want to try to figure out settings that are going to maximize this in a way that makes sense. One of the biggest traps you can get into early on is analyzing raw spectra. Please do not try to identify raw spectra, because that is a very advanced procedure and it very rarely works out. And it can appear like you have good signal or good correlations, even though you don't, just because the baseline is matching up well. So definitely pre-process your spectra whenever you're doing it. At the very least, just use the default settings by clicking this pre-processing tab. And I'd recommend going in and kind of fine-tuning them for what makes most sense with your spectra and the artifacts that you have, like we talked about before. All right, cool. So any questions? I'm going to pause again. Okay. Not seeing any questions coming in. So the last thing that we're going to do is we're going to download the matches. So this is kind of the product that you're looking for at the end of the day is your top matches. So we can download the top matches. And this will give us a data set of whatever the highest matches are from the spectral library. And I'll open that up and just walk you through how to analyze it. So in this data set, let's see, let me make that a little bit bigger. We have the most important things. I think the most important columns for you are going to be match value. So this is how strong the correlation is, the match threshold that was used, and whether or not you were above that threshold. So this will flag true or false if you're below that threshold. So this spectra is getting flagged right now as not a good ID. The signal noise ratio here and the threshold used for that, and whether or not you're above that threshold, and then whether or not you're above the combination of the signal noise plus the correlation. And hopefully with this data set, like your wheels are turning like, oh, okay, this is how I can apply this to my analysis. But if you have questions on how you can leverage this metadata better, please reach out. Always happy to talk about different ways to use the data. So we do have a spectrum identity tab. This is like the most raw form of the information from the library. And then a more useful form for classifying your materials is this one here. So we have the material class. This one, I've spent a lot of time fine tuning what the labels should be and adjusting them so you don't have like PE1 from a bottle cap as like one of your classes. You have polyolefins, and that's like anything that's similar to that is going to be put into that class. And so hopefully it's been really fine tuned for plastic pollution, but also I realize like some people are using Open Specy that aren't trying to do plastic pollution research. So if you have some of those kind of use cases and you want to use Open Specy to do, mineral analysis, right now, the classes are just getting lumped to mineral, but maybe you think that it would be useful to have, minerals kind of broken up into different groups. I would love to make that as an added column in the data set. So this one's going to be really useful, and then the ones up here in the front, the match value, match threshold, good correlation, signal noise, those are going to be really useful. And then all the other metadata is just whatever information we were able to grab while we were grabbing this library. We have about 20,000 spectra for FTIR from and 20,000 from Raman. I think right now we're up to like 40 different libraries that we've included in this free library. So yeah, it's really good, and it's been working super well. Yeah, it's made possible because of the vibrant Open Specy open source community. So thank you all for being a part of that. I don't have anything else for today. I know we have about like 3 minutes left. So if anybody has any questions they want to ask, feel free to unmute or write in the comments. Okay, used a different library, FTIR derivative, and did not get the same library type. Interesting. Let's see, FTIR derivative. And thank you for the questions. I'm not totally sure what you're asking, Julian. Maybe you could rephrase it. Barbara, do you have any recommendations for a good R tutorial? Yes, absolutely. Honestly, use ChatGPT to learn how to do R. It is so good. It will walk you through everything. I have data scientists in our group right now that started at like almost no R programming, and within a year, they're like better than me at R programming. So yeah, I would use ChatGPT, and I would tell ChatGPT, I'm a beginner in R. Give me a tutorial on how to use R from basic level, and then be like, oh yeah, and I'd like you to explain Open Specy to me. And it knows Open Specy. It knows how to drive Open Specy. So so yeah, there's a lot of good resources out there. I think that's the best one by far. Brittany asked, was the first session recorded? Yes, it was. It should be in the previous session. In the previous session Google Calendar link. If you don't have that, I can email it to you. Julian asks, in Excel column U, heading library type does not have the same class as yours. Huh, interesting. How matches column U, you said? Column U. Ah, this one. Okay, interesting. So the library type class, this is really, you can filter out libraries that are not relevant using this, like let's say minerals or something like that, that you don't want to use a mineral library. You can use this library type column to remove them. Hopefully that makes sense. If you're finding that you have different IDs, oh, okay, different column, okay. Yeah, and yeah, I will send out a link to the last video for anybody who wasn't here during that one. So happy to do that. I'll just send that out to the whole group, and I'll send that with the video for this one too. All right, thanks y'all. Hope you have a good day. There is another session. You might have a calendar invite to on Monday, and that's gonna literally go over the same exact thing. We're just doing that one at 8 p.m. so that way colleagues who are in like totally different time zone can attend also. So thanks a lot, and feel free to reach out if you have any questions afterward. I'll stick around for a little bit if anybody does have any questions that they want to continue talking about. But I'll probably head off here in a sec.